Goodness, I'm really late getting started. Sorry about that. I do want to make a fairly major announcement. I know y'all have been checking your emails very rigorously. No? Okay. If you had, you would have seen you got 2 emails recently from the college, from Miss Jamie Glass, by the way, is who it's from, though it doesn't say that, except down on the page probably, about the online evaluations for Lawson State. You saw those? Okay. Now, the first of them had a misleading subject line. It probably said something like, Lawson State Fall 2018 surveys have opened. When I saw that, I thought, how did I get this far back in my emails? I thought I was starting at the beginning, at the current ones. But then I opened the email, I looked at the date, and it was the current date, so I opened the email, and the email had been corrected, the subject line had not. Students have been notified that the summer 2019 term surveys are available, okay? They're telling us, please strongly encourage your students to complete the surveys. You are hereby strongly encouraged to complete the survey. Please do them. We value their responses, we really do. I like to look at mine to see where I need to get better, things I'm weak in, things I don't need to pay that much attention to anymore, that kind of stuff. But I'm also the math department chair. I use the evaluations of all the employees under me, full-time and part-time, to determine their annual evaluations, because the students get to see them a lot more than I do, and they get to see them in action, whereas when I enter the classroom, they can put on a pretty good show. But they get to see them on a day-by-day basis. So I really value these evaluations. Also, we're coming up very close to a SACS accreditation, your accreditation visit, and they look at these pretty carefully. So please do the student course evaluations. Now, I'm guessing that maybe only 1 or 2 of you have done one of these before here at Lawson, have you? Any of you done one before? No. Okay. If you go to the email, that's the easiest way to do this, because in the email there's a link. Click on the link, you go straight to the evaluations. Okay? If you don't do that route, I can tell you how to get there, but it's long and circuitous. So please check the email. Here is Tevin. All right. Just talking about student course evaluations for summer. And have you seen that email? Yes. You did? Fantastic. And you saw the link in the email, right? Yes. Just click on the link and you'll get right to the evaluations. Now, you still need to log in. This tells you how to log in, okay? Your login is your 7-digit Lawson ID number. Probably starts with a 120 or 121 or something like that, okay? Your ID number. Log in with your ID number. Then your password is your birthday, and that's an 8-digit numerical value. The first 4 digits are your year of your birth. For me, it would be 1951. None of you will be that far back, okay? Then the next 2 digits are the month of your birth. For me, it would be 01, January. Be sure to put 2 digits. And then the date of your birth, for me, it would be 07. Okay, if you have a 1 digit, be sure you put a 0 in front. Okay? And once you do that, you're in. Have any of you done an evaluation before? Here. You have here at Lawson? You have already done yours. Fantastic. Okay? How long did it take? 5 minutes. That's about what I've been hearing. Did you get asked to do any others besides just the course? Did you do any like registration or library or food service or anything like that? Occasionally you might get one of those, but more than likely you won't. But please do the course evaluation. That is really, really important. Of course, I get feedback from you every day that y'all are here, because I get to read body language and see if you're following and stuff like this. But a lot of these other places around campus don't get that immediate feedback, certainly every day. So please do whatever they ask you for in the student evaluations. Now, they will be open through the 8th of August. But on the 8th of August, y'all are going to be heading home or already home or going back to school, and you're not going to be thinking about evaluations here at Lawson anymore, are you? So please, don't put them off till the 8th of August. You're liable to forget about it. If you're liable to forget, do them early, just like Tevin did. Or you can wait and see what that final grade is, but as soon as you see that, or whatever it is going to make your determination, please do the evaluation shortly thereafter. Okay? All right. You got 5 now. That's enough for a basketball team. Okay. So, let's get started on the math. Any questions either about, yeah, was there a question?
Well, you said so if you don't do evals.
I'm sorry?
Wait to see the final grade.
I'm sorry?
What did you say about the evals and the final grade?
I said if you want to wait to see your final grade before you evaluate, you can. Or if you don't, if that doesn't matter, it's probably not going to be a deciding issue, do them early, okay? But if you want to wait and see what that final grade is before you do the evaluation, I understand you might want to do that. But if that you don't think is going to matter, go on and get them done. Knock them out while you're thinking about it rather than forgetting about it, okay? Now, any questions on either evaluations or calculus or anything else? All right. Where we left off last time was Chapter 13, Functions of Several Variables, and we were in 13.8, Extrema of Functions of Two Variables. We're limiting ourselves to, and I wish they'd say this more precisely, two independent variables. You're going to have a third variable, that's going to be the dependent variable, but it's going to be two independent variables. And example 3 is find the relative extrema of this function, f of xy is equal to negative x cubed plus 4xy minus 2x squared plus 1. Okay? Now, where would you begin? Boy, I know Monday was a long time ago, so I may have forgotten what we did then. Well, how would you begin? Not quite the gradient. We're going back to doing just the partials. Okay? Now remember what, let's go skip back and see. All right. If you have a function that has continuous second partial derivatives on an open interval containing the point AB, for which, so here's the key, the partial of f with respect to x at that point needs to be 0. The partial of y at that point needs to be 0. That is the key. Now, let me step back a few more because okay. Here we go. Definition of critical points. So the first thing we need to do is find our critical points. Here's the definition of critical points. If f is defined on an open region of R containing some point x0, y0, that point x0, y0 is a critical point of f if one of the following is true. The partial of f with respect to x at that point is 0, and the partial of y with respect to partial of f with respect to y at x0, y0 is 0. So that's one possibility. Both the first partials with respect to x and y must be 0. Or either the first partial of f with respect to x at x0, y0, or the partial of f with respect to y at x0, y0 does not exist. So the first thing we're going to do, take the partial with respect to x, take the partial with respect to y. See if we find the values for which they're equal to 0 or for which they do not exist. Just like we did for single variable calculus. You took the derivative, and if it existed, if it was 0 or did not exist, those are your critical values. Now we're calling them critical points because it's an xy point, not just a single x value. So the first thing we got to do, it'll take a while to get back there. Right here. First thing we're going to do is what? Let me get my pen set up. Okay. What did we just say? Partial with respect to which? Doesn't matter. Say x. Okay, let's do x first. Of xy. And that's equal to? Negative what? 3x squared. What else? Plus 4y. Okay, that's it. Now what does that partial need to be? Either 0 or doesn't exist. That's going to exist everywhere because x and y are defined everywhere, so we don't have to worry about not existing. Not existing would be if one of the variables within the denominator, if one of the variables in a square root or any other even root, or if one of the variables was the argument of a log. Those are the only places that we worry about where they don't exist. Here they exist everywhere. So what are we going to do? Set it equal to 0. Now, what does that say? That says that 4y is equal to 3x squared, right? Which you might want to rewrite as y is equal to, I can't write, 3/4 x squared. It has to be somewhere on the parabola of 3/4 x squared. That's going to be 0 everywhere on that parabola, right? Okay, that's not going to be good enough. What else do we need to know? Anything? What was the other condition? Help me, somebody. Anybody? Okay, you took the partial of f with respect to x. Say again? Yeah, let's do it with respect to y too. And what's that going to be? Somebody. Help me. 4x. 4y. And that has to be 0 because that's going to exist everywhere. There's no place it's not going to exist. We can simplify that a little bit by saying dividing everything by 4. Okay? And that would be x minus y equals 0, which means y is equal to x. Right? Yay or nay? Yay. All right. Yay. All right. Now, for both of these to be true, and they have to be, remember, both the first partial with respect to x and the first partial with respect to y must be 0. That means that these two must be equal. That 3/4 x squared must equal x. Right? Because they're both equal to y. Right? Now, I would move both of these to the same side and say, well, actually what I think I'd do is multiply both sides by 4 and say 3x squared minus 4x is equal to 0. Look reasonable? And now what? Now what? Oh boy, this goes back to algebra. You want to find the values of x that make that equal to 0. What do we do? Oh, come on, help me, folks. Say again? I can't hear. Okay. Okay. Now, completing the square is a legitimate maneuver here, but obviously you like to work way harder than I do. Okay? Huh? Okay, you might be able to do it that way, but guess what? Now, I don't know if I've told this class before, but what is the right answer if I say, what's the F word? And keep your minds out of the gutter, by the way. Factor. Factor. That's the F word in this class, okay? Oh, you did it? Say it louder. I can't hear. Okay, so how do you factor this? Second? How does it factor? Factor out an x, and what does that leave you with? A what? 3x minus 4 equals 0. Now what does that mean? Either x equals 0 or 3x minus 4 equals 0, and what does that produce? 4 or x equal 4/3. Perfect. Okay? Two possibilities for x. Let's plug them in and see. And since this has to be true, if x equals 0, then y is equal to 0. So there's one critical value, 0, 0. The other one would be when x is equal to 4/3, y must be 4/3. So there's the other critical point. Okay? Now those are the two places where both the first partial and the second partial are equal to 0. Right? Now, let me just check and make sure that's true. When x equals 0, y is equal to 0, that's obviously true. When x equal 4/3, then, yeah, 3/4 times 4/3 squared will give you 4/3. So, yeah, that's right. Okay. Now, we're not guaranteed those are, we know they're critical values, but we don't know if they're relative extrema. Now, how do we tell if they're relative extrema? The second partials test. Okay? We've already determined the places where the first derivative of the partial with respect to x and the partial with respect to y are 0. 2 points. 0, 0, and 4/3 worth. The test for relative extrema, consider this quantity. So what else do we have to do? Second partial with respect to x, second partial with respect to y, and the mixed partial, f with respect to x and then y, or y and then x. It really doesn't matter. So we've got 3 more partials to do. So let's go back and do, I'm sorry, that's not what I meant to do. Go back to this. So let's now do our f sub xx at xy. And what would that be? Take your f sub x and take it partial with respect to x again. What do you get? Negative 6. What do you say? X. Perfect. Let's do the second partial with respect to y at xy. And that would be, isn't that minus 4? Okay, minus 4. I thought that was what you said. Okay. Now we need to do the mixed partial. And it doesn't matter which one we do, they better be the same. So let's do f sub xy and see what that gives me. So you go to the f sub x, now take the partial with respect to y, and what do you get? 4. And let's also do the second partial and do first y and then x and see what we get. Get out of there. So let's do this one and take that with respect to x. And what you get? Say again? Okay, no, don't. Okay. These were things I did later. Okay. You get 4 again. That's a good thing to do because these two had better be equal to each other. If they're not, you probably made a mistake. Okay? That was just a check. Okay? Now we go to the second partials test. Okay? The second partial test is evaluate the quantity, consider the quantity f sub xx, f sub yy minus f sub xy squared. Okay? So, whoops, wrong way. So our test is d is equal to f sub xx evaluated at our point AB, which are these points up here, times f sub yy at AB minus f sub xy, or yx, it doesn't matter what you do, at AB, and you're going to square that. I like to put the square there. Okay, let's make sure we did it right. F sub xx at AB times f of yy AB minus f of xy sub xy at AB squared. Okay? Now, we got to do this for both points, so let's do it first for 0, 0. So your f sub xx at 0, 0 would be what? Okay, that's what we're evaluating first. What is f sub xx at x at 0, 0? 0. Okay, that was easy. Took a while, but it was easy. What's the f sub yy at 0, 0? It doesn't really matter, but what was it? Negative 4. 0 times negative 4 is 0, so it really didn't matter what the yy was, but minus, and what is f sub xy or yx, it doesn't matter which, squared at 0, 0. No. Either one of those. 16 minus 16. So we got 0 minus 16, which is minus 16. Okay? Now, let's go back and see what that tells us. If this d, which we just did, is less than 0, it is negative 16, then this is a saddle point. 0, 0 is a saddle point. Got it? Okay. So we know that this is 0, 0 is a saddle point. Okay? So that's not a relative extrema, because a saddle point means it's going down in one way and up in the other way. So it can't be an extrema. Extrema must be going up everywhere around or down everywhere around. It can't be going up in some places and down in others. So it's a saddle point. Let's check our other one. This is d at 0, 0. Let's do d at 4/3, 4/3. F sub xx at 4/3, 4/3 would be f sub xx at 4/3, x equal 4/3. It's not that hard, is it? It's got a fraction, I know, but that's not that bad. 3 will go in this negative 6. Second? Negative 8. You're absolutely right. Okay. Times f sub yy at 4/3. And what's that? negative 4 because it's that everywhere. Okay, minus, and what's your f sub xy squared? That was, again, your minus 16. It's 16, but you're subtracting it. Okay, so what does this yield you? That's 32 minus 16 is 16, right? Let's see what that tells us. If the d is greater than 0 and f sub xx is greater than 0. Well, let's go back and see. Yeah, I go the wrong direction. F sub xx was minus 8, wasn't it? Right here. F sub xx was minus 8. That doesn't fit. So we go to number 2. If d is greater than 0, which it is, and f sub xx is less than 0, then this is a relative minimum at 4/3, 4/3. So that's an extreme value. That's what we're looking for. This is a relative minimum. Okay, at that value right there. There's only one relative extreme, and that would be a relative minimum at 4/3, 4/3. Okay, you buy that? All right, let's see what they do with it. So let me erase all this ink. I hope I did it right. Begin by finding the critical points. That's your first step, and that means taking the partial of xy with partial of xy with respect to x. That's minus 3x squared plus 4y, which is exactly what we got. And the partial of f with respect to y at partial of f with respect to y, xy, would be 4x minus 4y, exactly what we got. They exist for all x's and y's, so the only critical points are those for which both those first partials must be 0. So we set each of them equal to 0. The first one tells us that we must be on a parabola. Well, the second one tells us here on the identity function of x equal y. And by substituting that into the first one, we obtain two solutions. Now this isn't maybe exactly like we did, but pretty close. And the x and y both are 0, 0, 0, and the x and y are both 4/3, 4/3, 4/3. So those are exactly the answers we got. And because f sub xx, second partial of f with respect to x both times is minus 6x. The second partial with y with respect to y both times is minus 4. And the mixed partial, f sub xy or f sub yx, we did them both, is positive 4. It follows that for the critical point 0, 0, that your f of xx would be 0, times f of yy minus 4, that's still 0, minus a 16, that'd be 0 minus 16, that's less than 0. If that's less than 0, by the second partials test, you conclude that's the saddle point. Now, we didn't identify the point. Now, we should have done that. We only did xx and yy. I mean, we did x's and y's. Let's figure out what the f at 0, 0 is. What's its value? Zero plus 0 minus 0 plus 1. So that's 1. So the point in question is 0 for x, 0 for y, 1 for z. Okay? So that's the point, that's our saddle point. We should have really said that back. I've already erased my stuff, but I wish I hadn't. Okay? So that's going to be at 0, 0, 1. That's the saddle point. Okay? We also need to do the same thing for the other one. So let's go back here and do it as well. F at 4/3, 4/3 is equal to, what's that one? Anyone know what 4 cubed is? $64. 3 cubed is 27 plus 4 times 4/3 times 4/3. Okay, right? Minus 2 times, what's 4/3 squared? 16/9, which we could have put there too, plus 1. Boy, we got some fractions to deal with now, don't we? Okay, so this is going to be minus 64/27 plus 64/9 minus 32/9 plus, I'm going to call that 27/27 because we're going to have to get everything to 27ths anyway, right? Okay, so let's first do 64 minus 32/9, and that would be 32/9. But we need to get it to 27ths, so we'll multiply numerator and denominator by 3. So that will be 96/27. Okay? So if someone wants to pull out a calculator, do 96 plus 27. That's going to be 123, I believe, minus 64. And I think that's going to be 79.
96 plus 27 is
123 minus 64. 59. So that'll be 59/27. Okay? So that's going to represent the point 4/3, 4/3, 59/27. And by the way, 59/27 is, doesn't seem right. Something seems squirrely here. No, it's supposed to be my, oh wait, no. We must have done something wrong, okay? This looks like a relative maximum. We said a relative min, didn't we? Well, I must have read the table wrong. No, we said relative max, didn't we? No, I said min, but I should have said max, because your D was greater than 0, right? And the f sub xx was less than 0, because it was a negative, okay? And if those two are the case, that meant your, let me go back here, less than 0, relative maximum. I think my eye just went to the wrong line. It is a relative maximum. And that makes sense here too, because at 0, 0, this is 1, and at 4/3, 4/3, this is greater than 1. So that can't be a minimum, because there's a point there. So here we have a relative maximum. And I think I wrote it down wrong. Okay, so this is a relative maximum, because it seems like I did write minimum. That should have been max. Okay? All right. Now, Okay, we got those two, we got that. Now, here's where we did our analysis. The D at 0, 0 was negative, which means the saddle point, okay, at the point 0, 0, 1. We went back and got that point. Okay, furthermore, the critical point at 4/3, 4/3, when you do the D there, this thing turns out to be -8 times -4, minus 16, which is positive 32 minus 16, which is 16. Okay, that's positive. Okay, but the second partial, I think I looked at the first partial before. The second partial was -8. Yeah, I looked at the wrong value before. The second partial was -8. I think I looked at the first partial. Yeah, that was my bad. Was -8. That means this is a relative maximum. Okay, meaning it's concave in a sense downward there because of this is negative, but the D value is positive, meaning it's going to be a relative maximum there. So this is sort of what it looks like. At 0, 0, 1, it's going down this way here, up this way there, so that's the saddle point, going down in 2 dimensions and up in the other 2 dimensions. And up here, though, it's going down in every dimension, so that's the relative maximum. Okay, and that's what it looks like. Thank you for drawing it. I would have hated drawing that value. Now, why they didn't label it, I'm not sure. They were lazy. Okay, all they said is it's they didn't label the point. We did. It's 4/3, 4/3, whatever we found at 59/27 or whatever. Okay. Now, all right. Absolute. Okay. Before we do that next thing, let's go and do example 4. Okay? Because this next slide is at the top of 945, and example 4 is the bottom of 944. So let's go back and do example 4. Maybe we'll do that without error, maybe. Find the relative extrema of this one. F of xy is equal to x squared, y squared. Okay? What you reckon we got to do first? Okay? Which one you want to do? With respect to x at xy, and this will be 2x, is that all? Y squared. Treat that as a constant, so that comes down. Next, F sub y at xy is equal to, second? Okay, 2x squared y. Now I like to put the constant in front. It doesn't matter. All right. Here we have Rachel. All right. All right. Now, what must be true about those two partials? They either both have to be 0 at a point, or either one of them may not exist at a point. Are there either of those not exist anywhere? No, they exist everywhere. The only things that make something not exist, if you have a variable in the denominator that could potentially become 0, a variable in a square root that could potentially go negative, or any even root, or a variable as an argument of log, which could either be 0 or negative, that can't happen. This has none of those. No denominators no square roots or any other roots, and no logs. Okay? So, where would these two partials possibly be 0? What values? Okay? Basically, this is equal to 0 anywhere along the x-axis where y is equal to 0, or anywhere on the y-axis where x is equal to 0. Okay? Anywhere on x-axis, okay, because then y would be 0, or the y-axis, because that's where x would be 0. Okay? So, x could be 0 and y could be anything, or y could be 0 and x could be anything. How about this one? Exactly the same possibilities there. Anywhere x is 0, or anywhere y is 0. So that would be anywhere on the x-axis or anywhere on the y-axis. Okay, that leaves a lot of points there that could be critical values, critical points. 0, 0 being 1, but anywhere on either of those two axes, I just wish, well, we'll leave it there, okay? Now, all right. Now, we need to narrow down some then, don't we? So what's the next thing we're going to do? F sub xx, is that what you said? Okay. Okay, xy is equal to what? 2. Say again? 2y squared. Perfect. And f sub yy is equal to okay, 2x squared. Okay. Sorry, I've got a stray line feed there that, or line that I didn't need to have. Okay. Sorry. Man, I either just got something in my eye or something, but I can hardly see. I'm glad it's my better eye, not the one I just had surgery on. That would really be scary. But okay. Now, all right. What else do we need? One more. F sub either xy or yx. I like to do them both just to make sure they're the same. What is f sub xy? Take the f sub x and take the partial with respect to y. What's that? Isn't it? No. It's 2 times, to take the partial of this, that would be 4xy. Right? Now let's do the same for f sub yx, just to make sure they're the same. What would that be? Take the partial of this with respect to x. 4xy. Good. They are the same. Now we feel nice and warm and fuzzy inside. Okay. Now, what's our test? Okay. Our test is to evaluate D. What's D? F of XX. Now, what we've got to do that is at every point on the x-axis, every point on the y-axis. But let's just do it a little bit now. F sub XX times F sub YY minus F sub XY squared. Okay? I didn't write all the things in because there can be a whole bunch of different points. Okay. Now, let's start with the x-axis. Where the x-axis is equal to 0, where on the x-axis the y is equal to 0. So f of xx, when y is equal to 0, is going to be 0. And f sub xy, where y is equal to 0, is going to be 0. So your d is 0, right? And you can plug in the others. On the y-axis, your f sub yy is going to be 0, because x is 0 on the y-axis, and f sub xy is 0 there too. So at all those points, your d is 0. And what does a d of 0 say? Inconclusive. We don't know if there is a critical point. We don't know if it's a extreme, a max, a min, or saddle point, or none of the above. There's no way to tell. Okay? Now, oh, I'm on the wrong page. I was going to say that looks nothing like our curve. Okay. Now, oh wait, I jumped the gun. No, I'm sorry. Well, we may get to the same answer, but you're supposed to actually do the calculations there. So f sub xx, let's put them in. I went on and evaluated, but I shouldn't have. Here we have 2y squared times 2x squared would be 4x squared y squared minus, and if you square f of xy, you get 16x squared y squared, right? And that gives you a minus 12x squared y squared. Okay. Now we should have actually done that, and the book did. Okay. Now, this is what we consider. Now, your d, anywhere on the x-axis where y is equal to 0 is 0. Anywhere on the y-axis where x is equal to 0 is 0. So all those places, this thing is 0. So this d is 0, which again means inconclusive. Okay, I should have waited till then to say it. Okay, now, however, because f of xy is 0 for every point along the x and y axis, f of xy, okay, we go back to the function here, the function, and we see that 0 anywhere on the x-axis where y is equal to 0, and anywhere on the y-axis where x is equal to 0. But at every other point, except the x and y-axis, every other point, this thing's got to be positive. Positive when x is positive, y is negative. Positive when x is positive, y is positive. Positive when x is negative, y is negative. Yeah. Every point, this is positive except on those axes. So basically, what we have is relative minima all along those axes. The test doesn't tell us that, but our knowledge of what this looks like tells us that. So this is an absolute minimum. You can call them relative minimum too, but they're absolute minimum. Because everywhere else they're positive, but on the x and y axis they're 0. and the function's 0. Everything's 0 there. All right. Now, at that point, we can go to the next slide, which is this one. Absolute extrema of a function can occur in 2 ways. First, some relative extrema. Okay, now we're talking absolute extrema. Okay, sorry. First, some relative extrema may also happen to be absolute extrema, like in the last problem we solved. But in the first example, if you go back, this was last time, not the first one today, but the first example 1 from last time, f of minus 2, 3 is an absolute minimum because I believe that was a paraboloid. Okay? So yeah, that was the absolute minimum of the function. On the other hand, the relative maximum found in example 3 is not an absolute maximum because that saddle point went way above it in other places. Let's go back and look at that one. That one right there. Let me clear my graphic here, my writing. And you see, this is a relative maximum, but look over here. Okay, not an absolute maximum. That doesn't have an absolute maximum. That keeps climbing forever. Okay, but it's a relative maximum here. There is no relative minimum. So absolute maximum can occur, like we just saw, with the. Okay, let's go back here. Example 1, where that was a paraboloid, that minimum, that vertex down there was absolute minimum. Okay? The maximum on the other one was just a relative maximum, not an absolute maximum. Secondly, the absolute extremum can occur at a boundary point in the domain, just like we did before. Now, we didn't set a domain for this one. If they had set a domain, if the domain would have been anywhere close by here, that would be an absolute maximum. The absolute minimum would have been somewhere down here. If the domain was up here, then some value up here would, I mean, you do your domains down here, then some value up here would be your absolute maximum. Okay? So it can occur on the domain, or it can occur at a critical point. And that's what they're saying here. Some relative extrema may happen to be absolute extrema. So if it's a critical point, it may also, we know it's a relative extrema, but it may also be an absolute extrema. Okay? But it could also be at a boundary point. And that's all they write. Okay? But they still do example 5 in the book. So let's go back and do example 5 here then. Find the absolute extrema of this function. F of xy is equal to sine of xy on the closed region. 0 is less than or equal to, x is less than or equal to pi, and 0 is less than or equal to y is less than or equal to 1. Okay. We want the absolute extrema. So what we've got to do here is 2 things, well, several things. We need to do the local extrema, which we've just been doing, which means first partial of each, second partial of each, and the mixed partials. Okay? Then we've got to consider our boundary values, where x is equal to 0, where x is equal to pi, where y is equal to 0, and where y is equal to 1. Okay? So we've got to consider all those places and see if any of them are relative minimum, or absolute max, or absolute minimum. So there's a bit to do. So what you want to do first? Anybody? A little louder? F sub x. Perfect. And what would that be? Second? Y times cosine of xy. Perfect. What next? Alpha sub y of xy, and that will be x times, whoa, wait. Okay. X times cosine of xy. Okay. Next. Anybody? Alpha what? XY, or you want to do that one next? That's fine. Okay. You got to do it at some point. This is also at XY. What would that be? Negative. Okay, if you're doing X first and then Y, you use this one and take the partial with respect to Y. Okay. Okay, if you do that, keep the Y and make a minus sign of XY, but then you're also going to have an X, right? Okay, now what you have to do is a product rule. Okay, you take the partial of this one with respect to Y, then it's if you're starting with this one, minus, the derivative of this is minus sine xy, chain rule, then x times y. It's the first times the derivative of the second. So you need the first, which is the y, times the derivative of the second, which is the minus sine xy, times the chain rule, derivative of xy is x with respect to y. Okay? Now let's just, for funsies, go on and take the partial of this one with respect to x. And what that, oh wait, we're only halfway through the product rule. The other half of the product rule would be what? Cosine xy, right? Because it's the first times the derivative of the second, that's what we've got here, plus the second times the derivative of the first. So we're taking the partial with respect to y. Now let's at the same time go back and see what we get if we take the partial of y and then x. So we'll take the partial of this one with respect to x. Okay? Yx. And I just do this to check it. Okay? That's going to be the first x times derivative of the second, which is minus sine xy times y. Okay? Plus derivative of the first, which is 1 times cosine xy. And guess what? That's exactly the same as this. These two are exactly the same. They better be. Okay? So now we've done what you requested, partial of xy with respect to xy. What's next? Second with respect to x. Is that what you said? Okay. Huh? All right. I thought you did. Okay. So alpha sub xx, and that would be what? Get out of there. What would that be? Basically, the partial of this with respect to x again. That's actually a little easier. Because guess what? It's not a product rule anymore. Because this is not a function of x. This is a function of y, so you can't treat that as a constant. So you're only taking the partial, with that as a constant, partial of this with respect to x. What would that be? Negative sine, is that what I heard? Some more. Y. Some more. Squared. You got it. Because you see, you treat this as constant, so you can't throw it away because it's a multiple of this. So it's y times minus sine xy, then chain rule with respect to x, another y. So negative y squared. Okay? Now let's do, what's the last one? Y. Why not? Okay? Now, take the partial of this one with respect to y. What do you get? Anybody? Negative what? Sine of xy? That's certainly part of it. What's that? Y squared. No, x squared. X squared. Because you're taking the partial with respect to y of this one. And this doesn't have a y in it, so that's just like a constant. The derivative of this is minus sine of xy times the derivative of chain rule with respect to y. That would be another x, so it's minus x squared sine xy. Okay. Now, what we're looking for is to remind ourselves, find the absolute extrema of that function. Now, where might they be? Absolute extreme. Second. Okay, let's not jump to the d yet. We've got to figure out where the first derivatives are 0. Right? That's going to be our critical values. Okay? So let's take it a step at a time. Set each of those equal to 0. Well, where is this one equal to 0? Obviously, any place where y is equal to 0. That would make that equal to 0. And the other thing is wherever xy is equal to pi halves, right? Where xy is equal to pi halves. Now, the reason I said pi halves is, notice that x and y are both positive only. Okay, so you can't have it being negative, okay? So you don't go do a minus xy. And x has between 0 and pi. So the product pair has to be pi halves, okay, because cosine is 0 at pi halves. Now, if you tried to go up to 3 halves pi, that's another place where cosine is 0. You know, let's see, can you get there from here? Then the product of xy must be 3 halves pi, but x can't be any greater than pi, and y can't be any greater than 1, so you can't get 3 halves pi. So I think that's the only possibility, where the product is 3 halves pi. Okay. Now, that makes for an interesting thing. Y is equal to 0 is the x-axis, okay? And the product of xy is equal to pi halves. That's going to be a part of a hyperbola in the first quadrant, okay? For instance, some of the points on there would be pi halves 1, pi fourths 2. No, y can't be more than 2. Okay. So yeah, you got some kind of bizarre points in there. Okay. And we'll come back to that in a minute. Okay. Because it has to be true that the second derivative is also 0 at the same points. So I'm sorry, not the second derivative, the f sub y. So that would be 0 anywhere x is equal to 0, or anywhere xy is equal to pi halves. Okay. Now obviously both of these agree xy equal pi halves, and the only place they both agree is when x equals 0 and y is equal to 0. So the point 0, 0, and the product of xy being pi halves. Yep, yeah, that's right. Okay, so those are the points in question. Now again, that product would be pi halves. I'm just going to draw the xy coordinates here. X is going 0 to pi, and y is going 0 to 1. Okay? Now, where the product is pi halves was either be here's pi halves here. So right here would be a point where it's equal to pi halves. And right here would be a point where it's equal to pi halves, across from right down there. And it would be sort of an arc in between those 2 points. That's it. Okay? Do you see how we got that? Okay? Because here the product of pi halves times 1 is pi halves. Here the product of 1/2 I can't write. 1/2 times pi is pi halves. And it would have to be some other product in between these two. So anywhere along that curve. The other place would be the origin. Right there. That's the only place where x equals 0 and y is equal to 0. Okay? And those would be the potential places where we have critical values. There's no place where these don't exist because sines, cosines, x's, y, they exist everywhere. Okay? So those are the possible critical values here. Then we've got all the boundary values, which basically is everything here, here, and here. Okay? And here. Okay? Those are your boundary values. Okay? So, let's go on and do our second derivative test, and this is what you were jumping to before. Let's figure out what our d is. D is what? Product of these two, f of x, xx, f of y. So that when you multiply those two together, you get x squared, y squared, sine squared of xy. Okay? Minus the f sub xy squared. Yeah. It's this thing squared. That's kind of a real pain in the neck. Okay? But let's go on and square it. That would be x squared y squared sine squared xy. Okay. Goodness gracious. Minus 2 xy, sine xy, cosine xy, okay, plus cosine xy squared. What a pain, a pill that is. But here's some good news, okay? This term and that term go away because one's positive and one's negative. So what your d is now that's going to be a plus now, 2xy sine xy cosine xy minus cosine squared xy. Okay, that's ugly writing, but I think it'll do. All right, now, boy, what a pain. Now, what we're interested in is where that d is positive, okay? And they could be relative minimum. Let me just take a look here and see. All right. We identified the right curve there where xy is equal to pi halves. It's a critical point. Okay. All right. So where that's true, where xy is equal to pi halves, let's go back and plug it into our original formula. F of xy is equal to sine of pi halves, because that's sine of xy. Sine of pi halves, well, sine of pi halves is 1. Okay? Now those could be relative max, relative min, or neither. We don't know that. Okay? And the only other critical point is 0, 0. And at 0, 0, and we identified that one too. Where was it? I wrote it down somewhere. Yeah, x equals 0, which is also y is equal to 0. So it's the point 0, 0. Yeah, I put it down here. That's where I put it. and xy is equal to pi halves. Well, xy equal pi halves, you know you're at 1 all along that, okay? At 0, 0, if we plug that in, your f of xy is equal to sine of 0 is 0. So it looks like 0, 0 could be a min. We don't know that for sure. And xy equal to pi halves, all along there, your z is going to be 1. So that could be a max. We don't know that either. Okay? Now, what you have to do from this point on is, now let's think about this carefully. Sine of xy everywhere from 0 to pi is positive, okay? And as long as the y is positive. X and y are both positive. X0 to pi is always positive. Y is always positive. So sine is always going to be positive. So there's a real good chance that is going to be your maximum, because that can't be any greater than 1. Okay? Sine is never greater than 1. And in this domain, it's never negative either. So that's got to be your maximum. Along that line is your maximum. Now this value, we know that you're there, where I thought I just heard it somewhere here. Your z is equal to 0. I know I said it, but I must not have written it down. Oh, here it is. Your f of xy is equal to 0 at xy is equal to 0. Okay? So you're at 0, 0. Okay? And it can't get any less than 0. I don't think we can, because your domain here is between 0 and pi and 0 and 1, so it never can go negative. So this has got to be an absolute minimum. This has got to be an absolute maximum, but we haven't determined if that's all. Okay? Now, we have to consider the other things on our domain. Okay? Now, in other words, all our boundary values. Well, the only place where this is even going to come close to being a 1 is at pi halves. Okay? But anytime the y is less than 1, that's not. So I think that's going to be our only maximum. That's going to be a minimum. So let's consider our own other minima. Okay? When x is 0, sine is always, when x is 0, so everywhere here, you're going to be a 0. So all along here is a 0, there's a 0. When y is 0, this is all a 0. Okay? And when y is pi. No? Okay. No, can't say that. Well, y is pi, and this is 0, you have a 0. So that and that. These are all zeros here, and I don't think any place else it can be 0, because any place else is going to be positive. If that's positive, this is positive. So our absolute zeros are along the two axes, and the absolute maximum, that's absolute minimum along the two axes, and the absolute maximum is along that curve there, that hyperbola. Okay. Now, yeah, and I think that's what they show here. Absolute minima, or their figure in the book is not very great in my mind, but the I think the figure is right. How they label it is a little poor. Okay. Now, I think we beat that to death. The figure, for those who don't have a book, let me show it to you. And I think it supports everything we were saying. One more value right up here. When x equal pi and y is equal to 1, then this is also pi, so it's a 0 there. It comes up to a max here, so it maxes here and it maxes there, because it's a 0 here and a 0 there. So it comes up to the max there, comes up to the max here, and then it's a max everywhere along there. So that's the one other place, 0 pi. I missed that one. No, pi 1. That's also a absolute maximum, okay? You don't get that from any of our analysis here, I don't think. Yeah, you do. I just missed it. That's where the sign is pi right there. The sign is pi right there. That's the only place. Everywhere else is between 0 and pi. Everywhere else here is between 0 and pi. It's also pi. So yeah, I missed that one. I don't know how we missed it in our analysis here. But it's there. Okay. I think we beat that to death. Okay. Oh, I was going to show the figure. That's when I solved the other point on this. All right. Here you have it. Let's sort of have it here. Here. You see, here's the... Goodness gracious. Here's where y is equal to 0. That's this line here. X equals 0 is this one here. And then the 0, 0 here, and of course there. And the maximum is along here. So it's going down from here and then down in that direction there. It's positive everywhere in this, along that rectangle. Positive everywhere, the max along that curve there. Okay, goodness, I can't hold that any longer. Okay. Now, homework exercises 3.8. Any of the odds 3 through 7, they're all at Calc Chat, 7's at Calc View. Any of the odds 9 through 23, they're all at Calc Chat, 9's at Calc View. Either 25 or 27, they're both at Calc Chat. 29's at Calc Chat. 31 or 33, they're both at Calc Chat. 35 or 37, they're both at Calc Chat. Any of the odds 39 to 45, they're all at Calc Chat. 39's at Calc View. Any of the do 47, it's a Calc Chat. You can look into doing either 49 and or 51 if you'd like. They're exploring concepts, but they should be at Calc Chat. 53 should be at Calc Chat, and then the true false 55 and or 57 should be at Calc Chat. All right, that's it for that one. All right, let's go and move to 13.9. Goodness, I keep saying 3.9. 13.9. Now, this again is a section that I'm not going to test you on, but let's sort of hit the PowerPoints just quickly, just so if you need it anywhere. And I think someone was going to be a industrial engineer, you thought? Yay or nay? Maybe not. Okay, I thought it was so. Maybe it was in a different class. Okay, let's pick up from the slideshow. And we're just going to go through these quickly. Don't worry about this. It's still Chapter 13, Functions of Several Variables. 13.9 is Applications of Extrema. Solving optimization problems for involving functions of several variables. Again, this is not that many people use it, but a few do. And we won't talk, I'll just show you method of least squares. The applied optimization problems, here is a situation. A rectangular box is resting on the xy plane with one vertex at the origin, that one back there. The opposite vertex, the one on this corner up here, has to be lying on the plane of 6x plus 4y plus 3z is equal to 24. That's this plane here. Notice it has coordinates of 4, 0, 0. That's when x is equal to 4, the other two are 0. That gives you 24. When y is equal to 6 and the other two are 0, that gives you 24. And when z is equal to 8 and the other two are 0, that gives you 24. So it's this plane that cuts through that triangular area there. Okay? So the box has to be on that plane and at the origin. It says find the maximum volume of the box. Okay? So what you're trying to do is find the maximum or the absolute extrema for the volume of the box given these constraints. That one point is there and the other point is at 0, 0, 0. Okay? Now we're not going to go into this in great detail, but just to show you how they do it, that x, y, and z represent the length, width, and height of the box. Okay? Which is fairly normal. That's what you're trying to maximize. So the volume of the box is, so one vertex in the box is on this plane and the other is at the origin. So if it's on this plane, you can rewrite that as z is equal to 8 minus 2x minus 4/3 z, or 1/3, okay, keep the 1/3 on the outside, 24 minus 6x minus 4y, 1/3 of that, okay? So that has to be the z coordinate, okay? So now you can write the volume of the box, x times y times z, with that as your z. So it's x times y times 1/3 this, minus that, okay? Well, I think I would go on and multiply that through, and that would be 8xy minus 2xyz minus 4/3. No, minus 6x squared y minus 4/3 xy squared. Okay? That was 8xy minus 2x squared y minus 4/3 xy squared. Okay? And they kept the 1/3 on the outside, that's fine too. Okay? 1/3 of 24xy minus 6x squared y minus 4xy squared. However you want to do that. Okay? Now, that's the volume of the box in terms of x's and y. What we're trying to do is maximize that. So we're going to do v sub x. You can do that one. I know y'all can all do it. Of course, remember this was xy in here. So it's minus 24. Now, the y is going to show up everywhere except I think they made an error here. Oh, no, I'm sorry. Yeah. I forgot. This was xy, x squared y, and xy squared. So there's an x in every term. So this is 24 this, yeah. So that's what that turns out to be. V sub y is going to be similar with that, okay? And you have the x in every term. So factor that out. Okay, now, go through the same thing we did before. Note that the first partial derivatives are defined for all x's and y's, so by setting v sub xy equal to 0, which we have to do, and solving for those equations, these two equations, each equal to 0, we obtain the critical point, so 0, 0, certainly going to be 1, 4, 0, 0, 6, and 4/3, 2. Now, I'm not going through and showing you how to get that, but they do. Now, pretty obvious to me, okay, and I think so to you too, if either x or y is 0, your volume is 0, okay? We don't, so go back here and look at this. If your y is 0, I'm sorry. That's what I wanted to go. If your y is 0, your volume is 0. If the x is 0, your volume is 0. So those are going to be minimum. So the only one that's going to make any sense for a maximum is going to be this one, 4/3 2. And you can almost stop right there and say, there you maximize the box. Let's see if they do, or they're going to test it. Yeah, they said at those three, the volume is 0, so they have to be minimum. So the only maximum could be at the other one. So apply the second partial test to it. Take the second partial and get that. Second partial y and get that. And the mixed partial and you get that. The next test? Okay. We probably aren't going to finish, but we might. We'll see. Did I just talk right through our normal break time? Y'all need a break? What you think? Yes? Okay. All right. Sorry. All that other mess took too long. Okay, let's pause this and we'll come back to... All right. So we found that the point there appears to be the only possibility for an absolute maximum. Okay? But let's check them by doing the second partial with respect to x. Now we have to go back to that form there, f sub x, and that's what it comes out. And the second partial with respect to x would be just this term, so it would be a minus 4y. Okay? I hope that's what they get. Yes, minus 4y. When you do the second partial with respect to y, yuck. Then here you would have a minus 8/3 x, because these two don't have any y's in them. So that's minus 8/3 x. And the mixed partial, and you can do either one of them, let's do both of them pretty quickly. Partial of this one with respect to y would be, oh boy, it's a product rule, isn't it? Oh, that's, probably easier to multiply that through. And this would be a 8 minus 4x minus 8y. 8 minus 4x minus 8y. Let's do this one with respect to x. This would be an 8 minus 4x, because this would be a 2x squared minus 4x, and that would be a minus 8/3 y. So yeah, that would be our mixed partial there. 1/3 of 24, okay, they like to keep that 1/3 out front. So 1/3 of 24 minus 12x minus 8y. Okay? Now, let's do the second partials test. When you multiply these two together, you get a positive 32/3 xy. Okay? We're going to plug that value in. And this one, minus, and when you square this, boy, that gets to be an awful looking number, doesn't it? So perhaps it's better to go and plug in the value, because you know what they are. So let's do that. I think that'll work at this point. That'll be a minus 16/3 times a minus 16/3, isn't it? No, wait, I'll go backwards. This will be a minus 8, and this will be a, minus 32/9. Okay, if you plug in the x there. Multiply those two together, it gives you something positive. And when you do this one and square that, it's going to be a mess. Oh, well, let's go and plug our values in and see if that will help. This will be a 16, right? 3 will go into 12 4 times, that would be minus 16, and this will be a minus 16 there too. Okay, that's minus 32. So this is going to wind up negative, but then you're going to square it. Okay, so minus 32 plus 24, that's 8, minus 8. Minus 8 thirds, square that, and you get minus 64 ninths. No, you get 64 ninths. Okay. So you go back and do the math. I'm not going to go through all that again. Let them do it, okay? And when you do that values, this is what I said here. Those two multiplied together, minus that one squared, you come out with something positive. Thank goodness, okay? If it came out negative, you have a saddle point and we got problems. But we got it positive, and this v sub xx is negative, and when v sub xx is negative, it's concave down, so therefore you have a maximum. So that will be your maximum. We said it had to be, okay? Hopefully it wasn't a saddle point, it wasn't. That is your maximum value, okay? You can conclude the second partials test. Maximum volume would be, well, you actually are interested in the volume, so go in and plug that in, and that would be 1/3 of 24 times 4/3 times 2 minus 6 times 4/3 squared times 2 minus 4 times 4/3 times 4. And when you do all that, you get 64 ninths cubic units, okay? That's your maximum volume, and that's going to be something in the order of, what, 7.7 you know, so cubic units. Note that the volume is 0 at the boundary points of the triangular domain of V. Yeah, of course it would be. All right. Method of least squares, we're not going to do too much with this. Many examples involve mathematical models. For example, a quadratic model for profit. There are several ways to develop such models. One is the method of least squares. In constructing the model to represent a particular phenomena, the goals are simplicity and accuracy. Of course, those often conflict. If you get too simple, you're not very accurate. If you're trying to get real accurate, you sometimes lose simplicity. So, for instance, of a simple linear model for the points here, okay? Here are points, 2, 1, 5, 2, 7, 6, 9, 12, 11, 17. They're generally going up, but not regularly. You want to get the best line that goes through all the points, so therefore the least deviations at every point, okay, in general. Well, you can't do plus or minus because that might wipe out and make a 0 somewhere. So you need to square the distance between the points, and that leads to some issues. And here's what you do. However, if you chose a slightly more complicated quadratic model, whoo, look how much better that fits. Okay? That's pretty nice. Okay? You could get maybe a little better by doing a cubic model, but I doubt it. As a measure of how well the model, y is equal to f of x, fits the collection of points, you can add the squares of the differences between the actual y values and the values given by the model to obtain the sum of squared errors. Okay? And that's what you get here. This is the actual y values, and this is your calculated y values. The difference of these for every point that you had, 1, 2, 3, 4, however many you had, square that, sum that, and then you're trying to find the minimum of those values. Graphically, S can be interpreted as the sum of squares of the vertical distance between the graph of alpha and the given points. And these are the vertical distances. Okay? If the model is perfect, S would be 0. However, when perfection is not feasible, which most of the time it's not, you can settle for a model that minimizes the least squares, the error, okay? For instance, the sum of the squared errors for the linear model that we showed earlier. Here's your linear model. They didn't tell you how they got it, but that's your linear model. And this is calculated when y is equal to 11, plug that in, and subtract 5 from it. And then the difference of that and 17, that's going to be the error there. Square that. This one's going to be a very small error. 1.9 times 9, and subtract 5 from that, you're going to be something awfully close to 12 just by this. This one's going to be quite a bit larger, 1.9 times 7, and then subtract 5 from that. See how that differs from x. It looks like that's going to be quite a bit more. This one's going to be pretty far off, and this one's going to be pretty far off, because you're doing the vertical distance, not how close it is to the line, but the vertical distance. Okay? Statisticians call this linear model that minimizes as the least squares regression line. And we're not getting into how to do that. In fact, you don't even know this, but I'm just showing you. This is another example of minimizing. Okay? Least squares regression line, look at that. Okay? Don't worry, we're not going to do this. Okay? But this is the formula you would get for it. There's your A, there's your B, and this is how they get least squares regression lines. Thank goodness we're not doing that. Okay. The x values are symmetrically spaced about the y-axis. Then, if they are, then the summation of x of I would be 0, so that wouldn't work very well. And then you can simplify this. That simplification is often possible with the translation of the x values. For instance, given that the x values for the data collection consist of 9, 11, 12, 10, 9, 10, 11, 12, and 13, you can let 11 be represented by 0, and then do this is minus 1 plus minus 2 plus 1 plus 2. You can do that kind of stuff and make the calculations easier. Okay? So this is almost the same problem, but done much simpler, and that simplifies your equations and everything. This is using the 4 points. So this is a slightly different problem. This is 4 points. So I'm not going into all this. There's your A. There's your A. There's your B. Weird looking numbers, right? And that would be the least squared fit for that. 8/13 x plus 47/26. Okay. Strange thing, but that fits those numbers really well. These two are almost on the line. These two are not far from it at all. Okay? And of course, the fewer points you have, well, as long as they're not wacko, then it's easier to get a pretty good fit. That's all we're going to do with that. That's probably more than we wanted to do with it. Okay? 1310, again, you're not responsible for this, but I wanted you to see it just sort of to be familiar with it in case you ever need it. And I'm not sure you will, but you might. And this is Lagrange multipliers. It's sort of building on what we just did, okay? But we're not going to. All right. Lagrange multipliers. There's another potential paper topic, folks. And by the way, did I mention papers? Did I mention papers? This is one of my best classes of all time. Guess how many research papers I have in? 0. As in 0. Oh, 1. Yeah, I don't have yours graded yet. Sorry about that. Okay. So let me make sure I have it. Oh, it's in the stack. Yeah, I think did you just give it to me? Oh. Let me see. Yeah, no, actually I have 2. I have Carlton's also. He's not here, and Jasmine, yeah. I've got 2, sorry. 2 out of the class size of 9. So it's better than some classes, but it's not great, okay? And guess what, folks? We only have no more than 3 weeks left. It may only be 2 or 3 weekends. Please work on your papers, okay? Especially those of that have more than one paper, right? Okay. All right. So, Lagrange multipliers, another potential paper topic. Who in the world was Lagrange? How did he develop this? Why did he develop it? How is it used? So we'll just quickly go through the method of Lagrange multipliers. Use Lagrange multipliers to solve constraint optimization problems, just like we were doing before, and use the method of Lagrange multipliers with 2 constraints. We'll just show that. We're not going to actually have to do it. So many optimization problems have restrictions such as constraints. That last one we did, it had to be at the origin and on that plane, on the values that can be used to produce an optimal solution. Such constraints tend to complicate optimization problems because the optimal solution can occur at a boundary point of the domain. In this section, we'll study an ingenious technique for solving such problems called the method of Lagrange multipliers. To see how that technique works, consider the problem of finding a rectangle of maximum area that can be inscribed in the ellipse x squared over 3 squared plus y squared over 4 squared is equal to 1. Okay? So we want the maximum rectangle you can put in there. Okay? So let xy be the vertex of the rectangle in the first quadrant, that one right up there. Now, because this is centered at the origin, then this will be minus xy, this will be x minus y, and this will be minus x minus y. So that's why we center at the origin there. Okay? Now, it has to be inscribed, so it has to touch on all 4 places here, and we're also wanting to maximize it. So this actually has 4 constraints, okay? Here, 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 and here, okay? And you're trying to maximize it. Because the rectangle has sides of length 2x and 2y, that's the other advantage of centering at the origin. The length here is 2 times y, because here's y and there's twice y. This is 2x, okay? Then the area is given by 4xy. 2x times 2y, which is 4xy. You want to find x and y such that f of xy is a maximum. That area is a maximum. That's what they call the objective functions. Your choice of xy is restricted to first quadrant points that lie on the ellipse here. Okay? And once you get the first quadrant, the others have to follow because you've done everything symmetric about that. So there is your constraint. Okay? Now, consider the constraint equation to be a fixed level curve of g of xy is equal to that. That's the constraint that you have to be. Okay? That level curve represents a family of hyperbolas that fit this. 4xy is equal to some k. In this family, the level curves that meet the constraint correspond to the hyperbolas that intersect this ellipse. Okay? This ellipse intersect that constraint. Okay? Moreover, to maximize f of xy, you want to find the hyperbola that just barely satisfies the constraint. Now that's a really Weasley type word. What do we mean by just barely satisfies? Well, we'll get to that. The level curves that does this is the one that is tangent to the ellipse, and that would be this one right here. Okay? Now they have a k of 24. Now they don't tell you exactly how they've gotten it yet. That's it. Here's the constraint. It has to be on this curve, okay? And you got to maximize your area. To find the appropriate hyperbola, use the fact that 2 curves are tangent to a point at a point if and only if their gradients, Kevin loves gradients, are parallel. This means that del f, which is your function, must be a scalar multiple of del g at the point of tangents. In the context of constrained optimization problems, this scalar is denoted by a lambda. That's lowercase Greek letter lambda corresponding to US letter or standard letter L. Okay, so we know that the gradient of f has to be some multiple of the gradient of g. The scalar lambda is called the Lagrange multiplier. The theorem right here gives the necessary conditions for the existence of such multipliers. That f and g have continuous first partial derivatives, have to have that, such that f has an extremum at a point x0, y0. F, which is our, what do we call it? I had a name for that function. The objective function. The objective function has to have an extremum at the point. Okay? Otherwise, you're not going to get an answer. On the smooth constraint curve of this, g of x, y is equal to c. So if your del g is not equal to the 0 vector, remember this is a vector, then there is a real number lambda such that del f is equal to the lambda del g. Gradient of f is lambda times the gradient of g. So the method of Lagrange multipliers by f and g satisfy the hypothesis of the Lagrange theorem, which we just had. Let f have a minimum or maximum subject to the constraint of g of x is equal to that c. To find the maximum or minimum value of f, use these steps. Simultaneously solve the equation, the gradient of f is equal to lambda times the gradient of g, and g is equal to g of x, y is equal to c, by solving the following system of equations. The partial of f with respect to x must be lambda times the partial of g with respect to x. Okay? The partial of f with respect to y must be lambda times that, and g of x, y has to be equal to c. Okay? Now, basically what you've got there is three equations, three unknowns. What are the unknowns? X, y, and c. No, x, y, and l. Lambda. No, I guess c. No, we know c. X, y, and lambda. Okay? Evaluate f at each solution point obtained in the first step. The greatest value yields the maximum of f subject to the constraint here. And the least value yields the minimum of f subject to the constraint here. Okay? So let's see if we can do constraint optimization problems. Okay? Find the maximum value of this. This is the one we just had. F of x equal 4xy, where x is greater than 0, y greater than 0, subject to the constraint x squared over 3 squared plus y squared over 4 squared is equal to 1. Okay? Now, to begin, let's do g is this. Okay? There's your g. That's equal to a constant here. So we're going to take this equation here and take the gradient of it. The gradient of this would be partial with respect to x is 4y I. There we have it. Plus the partial with respect to y is 4x j. Okay? There's your gradient of f. The gradient of g, which is this, is 2/9 x I plus 2/16 or 1/8 y j. Okay? So there it is. 2/9 x I with a lambda. I left off my lambda because the lambda's in here. 2 lambda x over 9 y plus y over 8 lambda j. Lambda y over 8j. Now, these have to be equal to each other, or at least a multiple of each other. So 4y has to be, and lambda's multiple, has to be 2. I would have put that lambda on the outside, but 2/9 lambda x, okay? And also 4x is equal to lambda yj, lambda y over 8. They don't show it yet here. But this gives you f sub x is equal. Partial of f with respect to x equal partial of lambda partial of g with respect to x. Okay? And yeah, here's the second one. This is equal to that. Okay. Now, frankly, in my mind, the better thing to do here is to write it as a linear equation, because it's all linear. And do this minus that, this minus that, and then see if we can do something to solve that equation simultaneously. And here's the constraint, that thing equal 1. Okay? So let's take either one of those, and you have to work them out and plug them in and see what you get. From the first equation, you obtain that lambda is equal to, and here we're solving for lambda here. Lambda is equal to, multiply by 9, so it's 36 over 2, so that would be 18 y over x. Okay? Down here, you would get 32x over y is equal to lambda. Okay? So the first one gave you lambda is equal to 18 y over x, and substitution in the second equation produces 4x is equal to that, so x is equal to 9/16 y squared. X squared is equal to that. Okay, substituting that value for x squared in the third equation then gives you this, so your y is equal to plus or minus 2√2. Okay? Now we're going to go through this in gory detail, but because that y is greater than 0, it fits, okay, fine. Choose the positive value, okay, that was plus or minus, we don't need the minus. Y is positive, so you choose a positive value. Plug that in and find that x squared is equal to 9/16 y squared. But y squared is 8, so x squared is equal to 9/2. So x is plus or minus 3 over √2. You don't need the minus, so 3 over √2. Now, that function is supposed to equal 4xy. So we plug this in for x, that in for y, see what happens. √2 obviously goes out. And that looks like it's equal to 4 times 6 is 24. And sure enough, yeah, is equal to 24. Economists call the Lagrange multiplier obtained by production function to be the marginal productivity of money, which is a strange name. For instance, the marginal productivity of money is lambda, and x represents the units of labor, y represents the units of capital. Then the marginal productivity of money would be this. This is just an example, and this is their formula for it. And it's a rather bizarre one, which means that for each additional dollar spent on production, an additional 0.334 unit of the product can be produced. Okay? If you just increase the dollar amount, you produce an additional 0.334 of a unit. Whew, goodness gracious. So, what if you have two constraints? Well, now you have two things here, lambda and mu. You can name them anything. For optimization problems involving two constraint functions, g and h, you can introduce a second Lagrange multiplier, mu, lowercase Greek mu for our m, so L and M, L, M, lambda mu. And then this is your equation where the gradient vectors are not parallel, as illustrated in example 5. Not parallel, okay? Here's example 5. Here's usually a temperature as a function of x, y, and z. There it is, represents the temperature at each point of the sphere. Find the extreme temperatures on the curve formed by the intersection of the plane x plus y plus z is equal to 3 and that sphere. Okay, I'm going to need a picture, I hope. Two constraints are here that you have to be on the sphere and here that you have to be on the plane. Okay, and you're trying to maximize the temperature which is up there. So your del T, your gradient of T is that. Your gradient of lambda times the gradient of G is that one. And lambda times, or mu times the gradient of H is that one. And here's the system of equations. Okay. This 2 is equal to 2 lambda plus mu. Okay. Next equation would be 2 is equal to 2 lambda y. I left off my x here. 2 lambda x, 2 lambda y plus mu. Okay. And the third equation is that 2z is equal to 2yz, 2 lambda z plus mu. Okay. There's our it's a system of 3 equations. Okay. And you have 3 unknowns. X, lambda, x, y, z. Okay. And you're using the lambdas. So the constraint 1 is the x squared plus y squared plus z squared is equal to 11. You solve this for x, solve this one for y, solve this one for z. I'll have it 2 places here. And plug it in there. And that gives you, and then your second constraint's there, and plug those in there. By subtracting the second equation from the first, you can obtain the following equation. Let's go back. This equation from that one, I think is the one we're talking about. You get 0 is equal to lambda, 2 lambda times x minus y is equal to 0. I think is what that gives you. Is that what you get? Yeah, 2 lambda is it times x minus y is equal to 0. And the other one is that one. Okay? And then there is your constraint 1 and constraint 2. Okay? So what you've done here is eliminate one equation anyway. From each equation you can conclude that lambda, from the first equation, lambda is either 0 or x is equal to y. Okay? I don't think lambda equals 0 is going to make a lot of sense here, so I think x is going to have to equal y. No, they're going to use that. Your critical points would be, and we won't go into that. You'd have to go back to your original equation and see what those are. So these can get really hairy. So let's just scroll through these. And we just don't have time to do those, sorry. And let's see, I think that was it. And that's it for chapter 13. All right. Now let's talk a little bit about your test. I passed them out to you. And one reason I'm saying this is for people at home, because I don't know if I got that recorded. I did pass out, this is the second test. It says test 3, I didn't notice that, because the last time I taught this course, we had another test before what y'all had, so this is your test 2. It says test 3, but it's test 2. Let me just quickly go through for you where you find these which sections you find these things located. Oh, you didn't get one. Anyone else who didn't get a test? Okay. Oh, nobody got a test. Did you get one?
I grabbed one.
You did. I give one to him. Okay. I knew someone picked it up, but I forgot that I didn't pass out the rest of them. Okay, this is chapter 13. Okay. I believe number 1 is from 13:1. Number 2 is from 13:2. Number 3 and 4 are from 13:3. Number 5 and 6 are from 13:4. Number 7 is from 13:5. Number 8 is from 13:6. Number 9 is from 13:7. And number 10 is from 13:8. All right. And you don't have any questions for 13:9 or 10. Okay? Any questions on that? All right. There's your chapter 13 test. We are through with 13. Now, if you need more problems to check on, under your calc chat, in your review exercises, I believe all these exercises have answers in the back of the book. However, calc chat has tutorial help and worked out solutions for the odd number exercises. Back of the book only has the answers. So again, I'll just give you the odds. Number 1's a calc chat, number 3's a calc chat, number 5's a calc chat, number 7's a calc chat, number 9's a calc chat, number 11's a calc chat, any of the odds 13 to 17 at calc chat, any of the odds 19 to 25 at calc chat, any of the odds either 27 or 29's a calc chat, 31 or 33's at calc chat, 35's a calc chat, 37 or 39's a calc chat, 41's a calc chat, 43's a calc chat, 45's a calc chat, either 47 or 49's a calc chat, 51's a calc chat, 53's a calc chat, and 55's a calc chat. 57's a calc chat, 59's a calc chat, 61 through 65's a calc chat, 67's a calc chat, 69 or 71's a calc chat, 73's a calc chat, 75's a calc chat, 77's a calc chat. Any of the odds 79 through 81 through 83 are at calc chat. 85 and or 87 are at calc chat. And wait a minute. Stop there. 83 is your last one. Okay? 83 is the last one. The rest of them are into 13:9 and 13:10. You can do any of those you want to, but you don't need them for the test. All right. Now, as I said when we started a little bit, one section in 11, and then did most of 12. You got that test. That was your first test. That was good stuff. It was vectors, that kind of stuff. But then, as I said before, to me, the meat of the course was chapter 13, partial derivatives, and chapter 14, multiple integration. And once we finish this, we'll do a little bit more in 15, which will be applications of kind of all this put together. So let's get started on 14. And we're going to have a tough time probably finishing 14 and even getting into 15, but let's give it our best shot. Okay? Now, chapter 14, as you saw, was multiple integration, and 14.1 is iterated integrals and area in the plane. Seems like we always start integrals with areas, and that's indeed what we're doing here. I went backwards. Okay, so our objectives in 14.1 are to evaluate an iterated integral. We haven't even defined what in the world that is yet. And we'll use an iterated integral, whatever that is, to find the area of a planar region. Okay, so what are iterated integrals? All right. Now, boy, without anything else, they jump right into something here. Now, notice what's happening here. They sort of jumped in full force without too much explanation here on the slides. Forget about the limits for right now, okay? What we're doing is an integral of a partial of f with respect to x times a dx, okay? Notice that the y is not involved with either this or that. There could be y's in there for sure, but to do the integration, we're only dealing with the x, okay? Now, so if you take an integral of a partial with respect to x times a dx, you're just going to get the function. It's sort of like the fundamental theorem of calculus part 1. If you take an integral, it undoes a derivative. And this derivative is with respect to x, and you got your dx there. So this is just going to give you your function f. But, whereas before these were numbers here, now they're variables of y. Because you see, the y hasn't come into the picture yet. So you're still going to have y's. They're treated as constant when you do your partial. They're treated as constant when you do the integration, because you're integrating with respect to x. So your constants are now constant functions of y. h1 of y to h2 of y. Okay? And so when you integrate this only with respect to x, you get some function of x and y again, and you evaluate, again, these are x's, where x equal h2 of y and x equal h1 of y. Because you see these limits refer to your x values. So this would be f of h2 of y times y, comma y, minus f of h1 of y. These substitute in from the x, y. So this is when you did an integral that was a partial with respect to x, and you're integrating with respect to x. If you're doing a partial with respect to y and integrating with respect to y, your limits are then functions of x. They're counted as constants, so these are the constants that you're going through. So your antiderivative of a partial derivative gives you the function, but you evaluate the y here at g2 of y minus at g1 of y. So f, the function f, not the partial, the function f, evaluated at gx, comma, g2 of x, minus f of x, comma, g1 of x. Okay? So in other words, when you're, just like when you're taking the partial derivative, you count of x, you count the y as a constant. When you're integrating with respect to x, you count the y as a constant. When you're integrating with respect to y, you count the x as a constant. Note that the variable of integration cannot appear in any of the, see the dx, that can appear in your limits of integration. If it's a y here, you can't have a y there. If it's x here, you can't have an x there. And so you wind up with just functions of x, of y here and x here. So this makes no sense to write. You can't have a integrate with respect to x and put an x in the limit. It doesn't make sense. You may have a number here, or you may have a function of y here, but you cannot have a function of x here if you're integrating with respect to x. You could have x's in here, no problem. You can't have them there if you're integrating with respect to x. Okay, they sort of jumped into the middle of that. So let's try one. Okay? What would you think, let me get my pen set up, what would you think just right off the top this might be? You're integrating with respect to y to xy. integrating with respect to y, you treat x as a constant. So what would that be?
Well, I know it would be 3y.
Okay, let's just first deal with this one. Okay? You're integrating with respect to y, so you increase the exponent of y by 1, right? You treat the 2x as if it's a constant. 2 is a constant, x you treat as a constant. You got 2x, and then you have y2 over 2, but that wipes out that 2 there, right? So that's the first term. How about the second term? Plus 3y cubed over 3, so you wipe out the 3 there. No x's there, nothing. Now you evaluate from 1 to x, okay? And you're evaluating, and I like to put down, at least to begin with, just to get you used to it. Remember, if you're evaluating an integration with respect to y, then this is y is equal to x, y is equal to 1. From that to that. So this tells you what to plug in for. Don't plug in x for x, plug it in for y. So this will be x is just a constant times, instead of y squared, you plug in x, so another x squared, okay, plus, plug in that, and that gives you, plug in for y, x, so that gives you x cubed, minus, plug in for y, 1, so that's again, and yuck, go to right x and right 2. Okay, that would just be an x times 1 squared, minus, because you're subtracting the lower one, 1. When you plug in y is equal to 1 and y cubed, that's what you get. So what do you have? X cubed plus x cubed minus x minus 1. And that would be 2x cubed minus x minus 1. Okay? Now, here's a little bit, something doesn't look quite right about it, but that is exactly right. Now, here's the issue we have. Back when we're doing single variable calculus, you could always take the derivative of this and get your integral. You can't anymore, okay? Because there's no y's left in here, and you have y's up there. So you can't do that anymore, okay? I was starting to say try it, but you can't. It just won't work, okay? So there's no good way, fast, easy way to check. But let's go back and see how they did it. So let me erase what I did. Can I erase, or y'all still writing? Erase? Okay. All right. Consider x to be a constant. Integrating with respect to y, you have x is a constant, so that's the 2x here, and that would be integrated with respect to y, y squared over 2. Well, the 2's go out. That just leaves you 2, or x y squared. And here, there is no x here. Integrating with respect to y, that would be y cubed. Because 3 times y cubed over 3 would be y cubed. But you evaluate that from 1 to x. Now, these are values of y. Remember that. So y is equal to x. You plug in here. Again, you treat the first x as a constant still. Plug in the x, and that gives you x cubed plus y, x cubed again, minus, plug in y is equal to 1, so you just get x minus 1. Or they put the x plus 1 after the minus sign. So that gives you 2x cubed minus x minus 1. Just like we did, done slightly differently. So here's how you do integration of more than one variable. Okay? Integrating with respect to y. Okay? But what if you had a problem like this? Now they've interjected here, we won't always have it later, but they've interjected here and put this in here, emphasizing you do the inside first and work your way out. So you first do this integral here, okay? The integral, the one we just did, right? From 1 to x of this thing dy. So we know what this answer is. We just got it, right? This will now be the integral from 1 to 2, the outer integral we aren't doing. What do we have here? 2x cubed minus x minus 1. Wasn't that it? Dx. Okay? That's just a regular integration. Notice, once you have integrated out the y's up here, you don't have any y's left, so now you're only integrating with respect to x. So don't put any y's back in here either. This last integral should only have numbers as the limit. Okay? So let's do it. And what do you have? That would be 2x fourth over 4, which would then be 1x fourth over 2, minus x squared over 2, minus x evaluated from 1 to 2. So let's do that evaluation. So this is x fourth over 2. So 2 to the fourth is, help me, 2 to the fourth is, what's 2 squared? And 4 squared is 16. 16 divided by 2 is 8, minus 4 divided by 2 is 4, minus 2, right? Now do the lower one, which would be 1 over 2, so that's minus 1/2, but then you do a minus, which would be a plus 1 over 2, and the minus of minus is a plus 1, right? Now, if you want to put parentheses in there and do it otherwise, that's fine, okay? Notice the good news here, both fractions disappear, okay? They add to 0. Now, let's add our positives together. 8 plus 1 is 9, minus 6 equals 3. What do we, oh! I must have blown one somewhere. I'm sorry?
8 minus
2. Okay, you may be right. 8 minus, 4 divided by 2. I don't know why I wrote 4. I said 2 and wrote 4. Okay. Nuts. Okay. So this will be 9 minus 4 is equal to 5. All right, good. Finally got it. Okay? Make sense? Now, let's see how they did it. Hopefully they did it correctly. Okay? Getting too big of a hurry here. Using the result of example 1, you already know what the inner integral is. That is 2x cubed minus x minus 1. Evaluate right? The integral of that with respect to x from 2 to 1, x equal 2 to x equal 1, 1 to 2, okay? So that'd be x fourth over 2 minus x squared over 2 minus x. Plugging that in, that would be 4. Boy, they sure skipped some terms, didn't they? 4 minus a minus 1, which is 5. They did all their evaluation here at first with 2's, so that would be 8 minus 2, which would be 6, minus 1 would be, no, minus 2 would be 4, minus a minus 1 would be plus 1 or 5. Okay. I like the way we did it better, even though I made a mistake. Okay. Now, the integral in example 2 is an iterated integral. Okay? The brackets used in example 2 are usually not written. I said they put them there just for emphasis. Instead, the iterated integrals are usually written as this. The inner integral is usually whatever the variable is here, those are the values here. This variable can't show up in either one of those. Okay. Now these functions could be constants. Okay. There's nothing preventing them from being a constant, but they could also have x's in them. Okay. They can't have y's in them. Okay. These here can only be numbers because you've already integrated out the y's, so the only things you can put there are numbers for the x. Okay. Or if you did it in a different order, then these here could be constants, or they could be functions of the other variable y. They cannot have x's in them, okay? And once you do that integration, you have only only y's left, and then you can integrate with respect to y, and those have to be numbers, okay? This is what we call iterated integrals. I'm not quite sure why they call them iterated. Maybe it's just a fancy word. I don't know. The inside limits of integration can be variable with respect to the outer thing, not with respect to the inner, variable with respect to the outer variable of integration. However, the outside limits of integration must be constant, okay, with respect to both variables of integration. You don't go introducing a y again, and you sure don't want an x because you can't have an x if that's what you're integrating with respect to. So the outside integrals are always, the limits are numbers. Okay? After performing the inside integration, you obtain a standard definite integral, and the second integration produces a real number. Okay? First integration probably will produce a function of your remaining variable on the outside. Generally it will. The limits of integration for an iterated integral identify two sets of boundary intervals for the variables. One for the inner and then one for the outer. Okay? Now, for instance, in example 2, the outside limits indicate the x lies in the interval from 1 to 2. So x is going to be somewhere between 1 and 2. The inside limits indicate that y lies in the interval from 1 to x. So it can go anywhere from 1 to whatever your x value is, and x only went as far as 2. So the y goes from 1 to x. Now that happens to be a 2 here, but we don't know that yet. I mean, you look up here. So those are the limits of integration. Together, these two intervals determine the region of integration R, which is of the iterated integral, which is shown here. So we're only integrating over this region. From y is going from 1 to x. Here's the line, y is equal to x. So 1 to x, whatever, I'm sorry. Y is equal to 1 to y is equal to x. So that would be the value y is equal to x. And then the second one is integrating from 1 to 2. Okay? So 1 to x means this, remember, is y is equal to x. Y is equal to x. That's that line. Y is equal to 1 is that line. And then this is x equal 2, x equal 1. Okay? So those are pretty obvious. Okay. I don't know if that picture is helpful. To me, it's not particularly. And I guess we're out of time. Let's see what the next slide is. Oh, area of a plane region. So we'll start there next time. Yeah. Okay. Now, homework exercises. We only did, what, 2 examples? So let's see. We won't have many. But it's a short section. I think you can do any of the odds 3 through 9. And then I think you can start doing any of the odds. Oh, and by the way, all those are at Calc Chat. 3's at Calc View. And you can do any of the odds. You can start doing some of the odds 11 through 27, I guess. If some of those seem a little foreign to you, hold off until we do a few more. But I think most of those you can do. Okay? And they're all at Calc Chat, 15's at Calc View. Okay. Yeah. You might even be able now that, no, okay. We'll leave it with that. Okay, good deal. Any questions? All right.
When is test 2 due?
I'm sorry?
Test 2.
When is it due? Technically 1 week from today, but more realistically before I give out test 3. Okay. But try to get it done sooner rather than later. Okay. Get started on it by Monday. So if you do have any questions about what I'm asking for, what does it mean, you can ask those on Monday. Okay. All right. Good deal. We'll see you. Have a good weekend. Now, of course, working on papers and tests will make it a good weekend, won't it?